Hi, this is Chang Han presenting our joint research work proposing minimal solutions to generalized three-view relative pose estimation. Unlike a classic pinhole camera whose projection rays from 3D points always intersect at the same camera center, a generalized camera configures multiple pinhole cameras and thus projection rays do not always intersect at the same point. One feature of a generalized camera is to make the field of view wider, enabling more potential features to be tracked. Examples of generalized cameras include AR devices such as Microsoft HoloLens or a multi-camera rig mounted on a drone or self-driving cars. The research community has made generalized two-view relative poses problem matured, which was shown to need 6 points for a minimal solution. Generalized three-view relative pose problem, however, has not yet explored, but has great potentials and advantages. Our paper shows that it only needs 4 points and suffers from fewer degenerate cases. Our contributions thus include proposing 2 minimal solutions to the generalized three-view relative pose problem using 4 points and 6 lines, using the state-of-the-art GPU-HC to solve the problem, and demonstrating its performances through extensive experiments. Our goal is to estimate the relative poses between generalized view 1 to 2 and 1 to 3. The underlying idea of the system for the 4-point case is that under rigid transformation, distances between 3D points are preserved. This gives 12 polynomial equations in 12 unknowns which are all the depths. Monodromy solver found that it has 583 solutions. After solving for the depth, recovering the relative poses is trivial. We can eliminate the translation part from the typical relative transformation equation to solve for the rotation part, and then back substitute to solve for the translation. For the 6 lines problem, the key idea is that planes passing through the projected lines in the camera center intersect at the same 3D line across 3 generalized views, giving us a constraint. If the rotation part is only considered, we get 6 polynomial equations in 6 unknowns, which the 2 rotation matrices are both represented by the Cayley parametrization. And there are 600 solutions founded by the monodromy solver. Plugging the rotations back to the original constraint solves for the translations, which is trivial as the translations are obtained from 6 linear equations. Since the existing group basis methods are unable to solve the proposed 2 minimal problems, we use homotopy continuation, or HC, tracking solutions from a known start system to an unknown target system by an iterative prediction and correction process. It is, however, very poor in efficiency, and GPU-HC is thus used. Beyond that, we further refine the numerical accuracy of the GPU-HC solution from single to double reduction using the LM method. In the estimation accuracy experiments, for noiseless case, both solvers provide around 10 to the power of -10 numerical accuracy, while in noisy scenarios, 4-point solver is robust. For the 6-line problem, noises were applied to the 2 endpoints of the line. Thus, the resultant estimations are sensitive to noise, especially when the line segment is short. Note that for the noisy scenario, it is a semi-pure translation, which is a degeneracy case for the two-view generalized relative pose problem. Comparison against the two-view, which requires 6-point correspondences, are given using the MAR-ReL dataset. The cumulative density functions for the rotation, translation, and scale clearly show that 3-view outperforms 2-view in robust estimation. In terms of speed, this table shows that how fast our solver could provide. Apparently, if using single precision, for the 4-point case, we gain more than 58 times speedup over the existing state-of-the-art HC solver, Julia, while for the 6-line case, more than 153 speedup is observed. This shows that under a ransack scheme, say 100 iterations, our approach is able to efficiently provide solutions in millisecond scale. This paper proposed 2 minimal problems to the generalized three-view relative pose problem and uses GPU-HC as a solver. Our code is available on GitHub. Thank you.